So we will continue with our treatment of equation of motion, Navier-Stokes equation, and apply it to different geometries the same way we were doing before. And before we end this part of the course, I would like to show you two more problems, slightly complicated, but nothing that Navier-Stokes equation and common sense cannot handle. So the specific situation that we have is where we have a cylinder, two coaxial cylinders. One is going to remain stationary, the other will be rotated. So let's say the outer cylinder is being rotated while the inner is kept stationary. So I have a cylinder which is stationary and another cylinder which is coaxial, but it's being rotated with some velocity, and the space in between the two cylinders is filled with a liquid. Now you can clearly see that how much force, how much torque in this case would be required to move the outer cylinder at a constant speed. Would depend on what kind of the liquid we have in between. So if you have a highly viscous fluid, we would require more torque, and if it's a very light fluid, very low viscosity, then it would be easy to rotate the outer one with the same speed. Now this suggests that measuring the torque of such systems where one of the two coaxial cylinders is being rotated with some speed while the other is kept stationary, this torque can be calibrated with the viscosity of the liquid. So in other words, if we know the viscosity of the liquid, if we know the torque, if we can measure the torque, we should be able to calculate what is the viscosity of the liquid. So this is a very common this is a quite common and accurate method to measure the viscosity of unknown fluids, unknown liquids. But before we can get up to that point, I need a compact expression that connects the torque with the viscosity of the liquid. So you, as a transport phenomena expert, you are given the job to find out what is going to be the torque necessary to rotate one of these cylinders while the other is kept stationary, and when we have a liquid in between, what is the torque required to rotate the outer cylinder. And obviously the torque, the expression for torque will contain, from our common sense we can say it should contain the geometric parameters, and by geometric parameters I mean the radii of the inner and the outer cylinder, the length of each of these cylinders, what is the density of the fluid, what is the viscosity of the fluid, and at what speed the outer cylinder is being rotated. So my goal for this specific problem is to find an expression for torque, the expression of which would contain, among other things, the unknown parameter viscosity. So measuring the torque, I should be able to measure what is the viscosity of the liquid. So this is a very good model to measure the viscosity. It's a very good model for some of the viscometers which measure the viscosity of certain liquids. Now when we talk about the viscosity measurement, the first instrument that comes to our mind is the capillary viscometer, where a liquid is allowed to fall through the very narrow capillary, and you know from your high school physics how to connect the viscosity with the flow rate, nothing but the Hagen-Poiseuille equation which we have derived. But this becomes problematic if you have a highly viscous fluid. If you have a viscous fluid to deal with, then in order to collect sizable quantities of the liquid to predict what is the flow rate, it would take a very long time. So for those liquids, you must devise other ways to measure the viscosity, not the capillary viscometer way. And the problem, the present situation that we are going to discuss and model is an ideal case to be used, ideal candidate to be used to measure the unknown viscosity of the liquid. So we are looking at the tangential annular flow of a Newtonian fluid. And the system in which this annular flow takes place is in between two cylinders, and I am looking at the top, and this one is moving with an angular velocity equal to omega naught. The inner radius is kr, the outer radius is equal to r, and the inner cylinder is stationary, the outer is rotating. And of course, you can imagine what kind of a flow profile it's going to be. So here it will have a higher velocity, and as you progressively come inside, the velocity will start to decrease. So this is the kind of velocity profile which you would get, and of course the velocity at this point must be equal to 0, since you have no slip over here. So here you have no slip, and in this point also you have no slip. So you can also write that VR and VZ both are 0. So it's 1D flow, that means liquid is only rotating. There is no velocity in the r direction, and there is no velocity in the z direction. So both in r and z direction the velocity would be 0. And since I do not have a pressure gradient, I also assume that there is no pressure gradient in the theta direction. So in the theta direction, you can assume it's almost like a Kweith flow, because in this direction the liquid is dragged in the theta direction because of the motion of the outer cylinder. There exists no pressure gradient to drive the flow, and since it's vertical, therefore this plane is parallel to the ground, therefore there is no effect of gravity in the theta direction. So there is no pressure gradient and no body force in the theta direction. The only motion of the fluid in the theta direction is initiated by the motion of the outer cylinder, which is rotating. So in that sense it's like a Kweith flow. However, there are some dissimilarities. The Kweith flow in this case is not in Cartesian coordinate system, and the separation between the cylinders is significant, okay, such that the Kweith flow approximation or the parallel plate approximation which we have done in the previous problem cannot be used in this case. So the two cylinders are sufficiently apart from each other, which does not allow you to use the approximation by which the cylindrical problem can be converted to a Cartesian coordinate problem. So we have to deal with the equation, with the cylindrical Navier-Stokes equation in cylindrical components. So I have three choices. One is the component equation in r direction, the component equation for theta component motion equation, and the z component motion. Now if you again think about this, since VR is 0, there is no motion in the r direction, okay. So the since the two cylinders, the bottom of the cylinder is blocked, therefore there is no motion in the z direction as well. So if you solve the r component of Navier-Stokes equation and the theta component of Navier-Stokes equation, you will simply get up the expression for the pressure gradient, because since there are no velocities, the entire left hand side would be 0. Since there is no velocity gradient, the viscous term would be 0. So what you get is, for example, for the z component, minus dp dz is equal to rho g. Okay. So rho in the z direction, since gravity is working, so therefore we will simply have, if I write the z component equation, the variation in the variation of pressure in the z direction is to be related by a body force, which in the case of the r component, in the case of the z component, will simply be the gravity. So dp dz and dp dr, the corresponding body forces, in one case it will be the centrifugal force and the other case it is going to be the gravity force. So these can be used to obtain the pressure, but these two expressions tell us nothing about the velocity expression. But my aim is to obtain the expression for velocity and somehow connect this velocity expression or the gradient of the velocity to the shear stress prevalent in the system. Once I have the shear stress evaluated from the known expression of velocity, I should be able to relate this shear stress to force and force to torque. That is the approach that we should take. So I start with an equation that upon solution would give me the expression for velocity. Once I have the velocity, I will find out what is the velocity gradient. If I know the velocity gradient, then I need to use the appropriate form for the stress of a cylindrical coordinate system, which is slightly different from that of the, which is not as straightforward as that of a Cartesian coordinate system. So from the velocity gradient and the expression for shear stress, I should be able to get the complete expression for shear stress, which definitely will contain the unknown parameter viscosity. Once I have the shear stress, I then multiply it with the relevant area to obtain what is the force. Once I have the force, I multiply that with the lever arm, in this case capital R, to obtain what is the torque. Now again, the viscosity that we had in the velocity expression, in the shear stress expression, in the force expression and in the torque expression will remain the only unknown in that expression. So if I can measure what is the torque needed to rotate the outer cylinder with some velocity, then I should be able to calculate using that expression what is the viscosity. Thus my aim is to obtain the velocity. In order to obtain the velocity, I need to use that component of Navier-Stokes equation in which we can foresee some motion, and for that the only direction in which there is motion is the theta component. So we must write the theta component of the equation of motion in cylindrical coordinate systems and try to see if we can obtain an expression for velocity. So that is what we are going to do next. So if you write the theta component of the NS equation, Navier-Stokes equation, the complete expression would be, which is available in your textbook as well, So this is the final form of the equation, and even though it looks ominous to start with, but you would see that after you cancel the terms, it's going to be very compact. So let's start with the first one, which is the temporal term. So this would obviously be 0 since we are dealing with steady state. So since it's a steady state case, then del v theta del t would be equal to 0. Come to the next term, v theta, variation of v theta with r, and I have a vr in here, but there is no velocity in the r direction, so vr would be 0. Here v theta is non-zero, but the del v theta del theta, this is equal to 0, so that which would simply says that, which is a statement of the fact that theta, the velocity, is not a function of theta. So if you fix the r, the velocity is not a function of theta. Velocity is a function of r, but velocity is not, if you fix the r, the velocity is not a function of theta. And here vr is simply going to be 0, and in this case vz is going to be equal to 0. We have mentioned, we have assumed that there is no pressure gradient in the theta direction. So it's simply, the outer one is simply rotating. There is nothing to force the liquid, no pressure gradient to force the liquid to move in the theta direction. So therefore this is going to be equal to 0, and v theta is a function of r. V theta here is a function of r, so I cannot neglect, I cannot make a statement, I cannot neglect this term. So this term will remain in the governing equation. If I move to the next term, v theta is not a function of theta, so this would be equal to 0. Then there is no question of vr, so this part is going to be equal to 0, and v theta is not a function of z, so this is going to be equal to 0, as well as there is no body force, no component of g in the theta direction in a vertical cylinder, therefore this will be 0 as well. So what you see from here is that from the entire equation, the entire Navier-Stokes equation, theta component of Navier-Stokes equation, all terms are 0, and you get the governing equation of out of this to be 0 equals d dr of 1 by r d dr of r v theta is equal to 0. So this is your governing equation, and look at it, look at how easily you could obtain this governing equation, starting with a general equation that takes into account all possible variations. But you do not have these many complications, so you can directly get from the theta component of Navier-Stokes equation what is your governing equation. Now think of the difficulty or the potential for errors if you are going to imagine a shell around this and try to figure out what are the momentum, in term, out term, shear stress, pressure, gravity, and so on. So here you do not have to do anything. That's the beauty of Navier-Stokes equation. You start with the equation, cancel out the terms that are not relevant, and you get a very compact expression in a matter of minutes. Okay, and you can never be wrong through if you use Navier-Stokes equation. So with this equation, we are now going to work on this equation to obtain what is the velocity expression. So you start with we started with the expression that 0 is d dr of 1 by r d dr of r v theta is equal to 0, which upon integration would give you v theta is c1 by 2 r plus c2 by r, and the two boundary conditions are the no slip conditions, that is at r equals kappa r, v theta is 0. So r equals kr, this is essentially the inner cylinder, whereas at r equals capital R, v theta would be equals the angular velocity times r. This is what you have on the outer cylinder. So the expression for velocity and the boundary conditions would when you put these two together, you obtain the expression of v theta to be omega naught r kr by small r minus r by kr divided by k minus 1 by k. So the velocity is a function of the imposed condition, which is the velocity with which the outer one is being rotated, and all the rest are geometric parameters, and so therefore v theta is a function of r. Now, as I mentioned to you before, is what we know as the shear stress for a simple Cartesian coordinate system will have slightly different form because of the transformation from a Cartesian system to a cylindrical system. So the expression for shear stress in a cylindrical or a spherical coordinate system would simply not be equal to mu times the velocity gradient. There would be other components present in it, and in any text you would see what is the corresponding form of the equation, corresponding form of the shear stress for cylindrical coordinate systems and for spherical coordinate systems. Here you would see that the non-zero component of shear stress, the velocity is in the theta direction, and the theta component of momentum, because of the variation in velocity in the r direction, would get transported in the r direction. So tau has the first subscript to be equal to theta, because theta denotes the direction, the momentum, the theta component of momentum, which is non-zero in this specific case. So theta is the direction in which you have velocity. So theta is the direction in which you have momentum. Due to viscosity, this theta momentum gets transported in the r direction as the velocity varies in the r direction. Velocity doesn't vary in theta direction, so therefore tau theta is 0. Velocity does not vary in the z direction, therefore tau z theta is 0. However, since velocity varies in the r direction, tau r theta will be non-zero. So the only shear stress expression that you should read, you should find out from your text, is the expression of tau r theta from your textbook. So once you have the expression of tau r theta from your textbook for a cylindrical system, then your job is done. And that tau r theta expression for tau r theta will contain the velocity gradient. The theta component, the velocity, theta component velocity gradient of that. So the job is to identify which tau would be non-zero, which is simple in this case, and find the expression of that tau from your textbook, and then plug in the expression of velocity which you have obtained by the solution of Navier-Stokes equation. So let's see how that is done. So here what you have is the expression for velocity, and you realize that tau r theta is the only non-zero tau that you have in this system, and from the text you know that you would be able to see that tau r theta is mu times r del r of v theta by r plus 1 by r del v r by del theta. So this is the expression for tau r theta for a cylindrical coordinate system, and here you know that Vr is 0, so therefore this is going to be equal to 0. So your tau r theta would simply be equal to the first term. So this would be the expression for tau r theta, and in this expression you have to put in the expression for v theta in here and do the del r of that, and this would look like as mu times r d dr. No need to use the partial signs in v theta is a function of r only. It's not a function of theta or of z. And then what you get is so this is the expression that you would get. And once you do this, I will skip the intermediate steps as they do not require any more understanding part. Tau r theta final expression would be minus 2 mu omega naught r square 1 by r square times kappa square minus 1 minus kappa square. So this is the expression for tau r theta. The torque T required to turn the outer shaft is equal to the force. The force would be tau r theta, but it is evaluated at r equals capital R, since it's the torque needed to rotate the outer shaft. So this is tau r theta, and since this is on the fluid, on the shaft would be minus of tau r theta multiplied by the area, which would be equal to twice pi r L. So this is area, this is stress, and so together its force, and it should be multiplied with the lever arm, which in this case is r. So this expression for tau r theta is then plugged in here, and you get a compact expression of tau as 4 this is the final expression for shear stress for torque that you would obtain. So this is a very good model for friction bearings, and the viscometers which are based on this expression or this concept are known as Kueth-Hatschek viscometer. So what we have done so far is we have obtained an expression for torque when we have two cylinders, one is kept stationary, the other is the outer one is being rotated, and the torque expression contains the geometric parameters which are L, R and kappa, the operational parameters which are omega naught, and the property of the fluid, property of the liquid that is of interest as tau. So once T is measured, the torque is measured, the velocity, the geometry, the length, etc. are known, then the only unknown mu in this case can be accurately calculated. The viscometers which are based on this principle are known as Kueth-Hatschek viscometer. There is only one more thing to add before we close the discussion on rotating viscometers, the viscometer where one is rotated. Here you have seen that the inner cylinder is kept stationary, the outer one is being rotated. What happens if we do the reverse way? That is, the outer is kept stationary, the inner is being rotated. If that is the case, then also this formula or slight variation of this formula will still hold, but the expression that we have obtained for this specific case, let us review what are the assumptions that we have made in this. The first and the prominent assumption that we have made, that it is one dimensional steady state laminar flow. The moment you start to rotate the inner cylinder, keeping the outer cylinder as fixed, the packets of fluid will have a tendency to move towards the outer edge across the flow, because the packets of fluid which are close to the rotating inner cylinder, they have a high velocity. What they see next to them is a region of low velocity. So the tendency of that fluid packet, faster moving fluid packet, would be due to centrifugal action to move towards the outer edge across the flow. When that happens, the straight streamline nature of the flow is going to get disturbed, and our assumption that our assumption of laminar flow will be put into severe test. So in order to maintain the assumptions in the system, it is always customary to rotate the outer one and not the inner one, such that the laminar flow can be maintained for a longer duration, for a higher value of omega naught, higher value of the rotational speed, and you can still use the expression to obtain what is the unknown mu. So the applicability of this relation in terms of laminarity would be sustained to a higher value of omega naught if the inner cylinder is kept stationary and the outer one is rotated. So that's something one has to keep in mind while working with viscometers, where one cylinder is kept stationary, the other one is rotating. It's always the outer one which rotates and not the inner one. Thank you.